right, everybody. Thanks for joining us. Our speaker today is Dabaliswar K. Panda, but we all know him as DK, so that's how I'll refer to him. DK is a professor and a University Distinguished Scholar of Computer Science and Engineering at Ohio State University. He's also a fellow of the ACM and IEEE, a recipient of the 2022 IEEE Charles Babbage Award, the 2024 IEEE TC/PP Outstanding Service and Contributions Award, and he has published over 500 papers. DK leads the research group that develops the MVA Pitch MPI libraries, which are being used by more than 3,400 organizations worldwide in about 93 countries and growing. We use MVA Pitch at SDSC. I used it in my dissertation, so we're all quite familiar with that. And there's been more than 1.9 million downloads of this software, and it empowers many clusters that make it to the top 500. So if you're in HPC, you're going to know a lot about MVA Pitch. But DK also serves as the director and PI of the NSF-AI Institute, the Intelligent Cyberinfrastructure with Computational Learning in the Environment, or short term is ICICLE. And that's the topic of his presentation today. So with that, thank you so much, DK, for finding time to join us and give a presentation. And I'll turn the sharing and talking over to you.
Thank you. Thank you, Mary, and Cindy also. Good afternoon from the East Coast. Good morning in the West Coast. Let me share my slides and we'll keep moving. So it's a pleasure to present in this seminar. Thanks again, Mary and Cindy and other organizers for inviting me here. As I was introduced, today I'll be focusing on this AI Institute, which I'm leading. SDSC is actually our partner also. Very soon you will see that. And the focus is like how to really design intelligent cyber infrastructure for computing continuum. I'll introduce that very soon, and then provide an overview of the activities of the NSF-AI Institute. Now, even though I'm talking here, I'd like to first provide credits to all the ICICLE team members, and those at SDSC might be seeing this photo is actually taken from the SDSC computing center. We had our all hands meeting almost 1 year. The time has very quickly passed. So we had taken this photo there. So the credit goes to all the people, the hardworking staff, faculty, students who are making this very successful. Now, if you take a very high-level view of where the computing is heading, we need to take a look at the past also. So go back almost like 50 years. This is where the scientific computing or high-performance computing started. In 25 years, around 2000, the big data analytics came. So we had computation, we had data. So people wanted to make more sense out of the data. And then through that process, all different kinds of analytics came and people wanted to learn things. And this is where it gradually moved into the HPC plus AI field, where we are very actively in this field for the last 10 to 15 years. But while this is happening, we also need to take a look at it where and how the data is being generated and processed. So that is coming as a difference. So if you take a look at the left side, that is the kind of the traditional model where you collect the data, you take the data to an HPC center, and then you perform your scientific computation, AI, and big data work. But if you take a look at the right-hand side, that is the new way where data is being generated, and we call it like a computing continuum. That means if you can see, like the data is being generated by sensors, data is being generated by IoT devices, by drones. But then as the data is coming, they are being streamed. We also want to perform very similar kind of things. I mean, it's the AI operations, the data analytics, as well as the scientific computations. So that leads to a challenge saying where and how you want to do it. And so that the entire system, the workflow actually works in the best possible manner. And then the design can be scaled to different scenarios. So one example, I'll go into more detail. This is actually one of the use-inspired science cases for ICICLE is AI-driven digital agriculture. Of course, agriculture has been there for since the human beings have been there on the earth. But over the years, as the technology is advancing, people are actually trying to utilize the technologies in the schemes to make improvement. And then the question is, okay, how AI can be used? So very simple thing. We'll see more complex scenarios later on. So let's say we have a field with some crop kind of, let's say soybean, and then we have some diseases in the field, which normally happens. Now, of course, traditionally the farmer can actually go in a truck or a tractor, visualize, and then decide that, this part of the field has disease one, this part of the field has disease two, and then we'll be spraying appropriate pesticides. Now the question is, instead of doing this manually, can we actually try to utilize all the very latest AI technology? So for that soybean crop and all different kinds of diseases, if we have a lot of images, then we can actually build an AI model. And once we build an AI model, that AI model, we can actually put it on a drone, and then the drone can actually fly and then trying to do a real-time inferencing. And it can actually give you, in the end, is a heat map or a shape file, which exactly tells in that field where diseases have happened. And then that information can again be given to either an intelligent tractor or a specialized drone, which has like a spraying capability, so that they can go and then precisely do the spraying. So if we can achieve that, gradually you will see like this will be the duration or the time duration for identifying the disease and solving it is much more faster. But at the same time, the way we do precision spraying can actually help the environment, and we can actually lead to very good yield of the crop. And depending on like how these additional services cost and all, we might be able to also save a lot of money. Another kind of scenario is like a supply chain management. And many times we know like a let's say all kinds of hurricanes come in the East Coast. We have seen like many times in the West Coast, like Freeway 5, wildfires are coming. California, especially with a lot of fires. So in that kind of emergency scenarios, there is a lot of immediate issues come. What to be done with the food supply chain? Like if you are a government person or a municipality person or a shopkeeper, very quickly you want to know what to do in the next 24 hours or 72 hours. So can AI help you? They are this kind of thing. And these are again, this is also another example of how use inspired science cases. I'll try to bring it again later. But these are some of the motivational scenarios or societal problems what we want to actually solve through AI. But from a technical angle, as you can see, I introduced this computing continuum. So the broad idea is that as the data is moving from sensors to edge device to cloud or HP centers, we need to identify how to define this workflow and take appropriate steps in every step so that the data movement and control we are trying to optimize. And at the same time, we are trying to harness the heterogeneous computing power. And that is the very broad challenge of ICICLE. So how to create this intelligent cyber infrastructure for computing continuum in the modern AI era. And at the same time, the second objective of our institute is to democratize these solutions. So that means we want to continuously lower the barrier of these solutions, what we create, so that more and more people can start using it. Okay. For example, like the agriculture example I said, the entire workflow we can actually generate and then put it into an iPhone as an app. In that case, the farmer can actually subscribe with a $9.99 per month, and he or she can exactly to the morning ask a question, okay, what has happened to my field? Where should I be spraying? Should I harvest today? So like this, a lot of kind of questions, even in a conversational AI manner, the farmer can actually interact with our bicycle system. And that's how we want to make our solutions or take our solutions to the end users. Now, of course, this is a 100,000 feet view. But now if you really go down, trying to take a look at the computer science challenges, these are all the boxes you will see. Like how do you do efficient data collection cleaning? How do you do model training? How do you run the inference in the S2 center, in the cloud computing continuum? How do you actually build these kind of models and data commons? How do we achieve the end-to-end workflow? How do we do resource scheduling, conversational AI support, privacy preserving techniques, and of course the reference architecture. So these are the kind of the very under the hood we need to come up with innovative solutions. And that's what ICICLE has been doing for the last 4 years. And not only we are able to solve our like a 3 use-inspired science cases, but we feel that this kind of solution, what we are developing, will enable kind of a newer workflows in mobility, materials, manufacturing, biotechnologies, different kinds of AI systems and test beds, because all the components we are able to actually integrate it together. So this is the little bit very high level overview again of the ICICLE. That is the focus as I indicated, like how to create intelligent cyber infrastructure. This is the QR code and the main website is icicle.ai. I want to also indicate that over the last 5 years, US National Science Foundation has invested in 29 of such institutes. And each institute is like a $20 million budget over 5 years. And every institute has a very dedicated focus. You can think of like for, let's say, AI for climate, AI for physics, AI for material science, foundational AI. But the ICICLE is the only one which is focusing on the cyber infrastructure, like how to really design it. Okay. And later on, I'll try to show you that our infrastructure can actually be used by all these other AI institutes and also other HV centers. And we are already gradually collaborating with many of them along that aspect. So this is the very broad picture. We saw like the computing continuum at the bottom. I motivated digital agriculture, smart food sets. We also have the third pillar, which is our use-inspired science cases called animal ecology. And this is where we are trying to do the co-design. So the intelligent cyber infrastructure, the ICICLE stack is actually in the middle. And we actually, in our team, in addition to computer scientists, we have actually our faculty, staffs, and students from all these disciplines, user disciplines, the agriculture, the food sets, animal ecology. So we have taken their requirements and translated those requirements into the ICICLE infrastructure. And I've been actually deploying into their use inspired science domains and trying to get feedback saying how actually these systems are enabling those use inspired science case scientists to really do their jobs in a much more efficient manner and with an AI enabled manner. So this is a very large organization, as you can see, coast to coast. Ohio State is the lead. I am the lead PI, but there are almost like here, if you see, 16 organization, 23 faculty, 29 staff, almost 60 students from PhD to K-12. All of them are working together. And as I said earlier, SDSC is also one of our partner, and these are all our collaborators. So this is how it's a very large team. And especially since we were funded from the NSF Office of Advanced Cyber Infrastructure or OAC, as some of you might be knowing, in addition to research and publications, another big mandate for our institute is to really have the software being developed and be available. And that's what I'll be talking later on. All these components, whatever we have developed in 4 years, all these are available with end workflow, and you will see real demos, end-to-end workflows kind of things working. So if anyone of you are interested, you are free to download these tags. Some of them are also available as AI services. I'll talk about that towards the end. Now, we have also gone global. As you know, for example, agriculture is not just a problem in US, it's a worldwide problem. So we have been some collaboration going on with IIT Bombay in India on a very similar issues. But even though you say that it's a similar issues, but the fundamental solutions might be different. In a way, let's say in the Ohio, we are focusing on soybean. In India, we have to focus on rice. So even the principles and the concepts are the same, but the AI models are different, and how you interact with the communities are different. So that's how we are trying to go back and forth in the translation process. So this is the very high level overall vision. As I mentioned earlier, like just a minute, something popped up on my screen. Let me. Uh, okay, sorry for the. So this is our stack. And what you will see that we have like a foundational systems AI, then within this intelligent cyber infrastructure, we have CI, that is cyber infrastructure for AI. We also have AI for CI for AI. That is a very interesting thing. I'll touch a little bit about that. Of course, software architecture, visual analytics, explainability. Also, there is a big focus on privacy, accountability, and data integrity. And all these components, as you can see, and that is the focus of this talk, that we have been designing a lot of co-designing here. Okay, because if we just build this stack in a vacuum, we are not very sure whether it will work or not. So we have been going co-designing with these three different use inspired science cases. They have different kinds of computation, communication, IO, networking, and AI requirements. So that's how we have chosen all these things. And then this entire stack actually interacts with the end users through conversational AI. Okay, that is the kind of the goal. And now, if you go down in each one of these, this is a very complex slide, but I just want to uh, give you a sense of that complexity. So, for example, if you take a look at the foundational systems AI, which is one of the thrust, below that we have a lot of sub thrust, like a knowledge graph. How do you create knowledge graph, model commons, adaptive AI, the federated learning, conversational AI. So, like each thrust has multiple sub thrust, and again, under each sub thrust we have multiple topics. Okay, so that's how actually the team has been completely working together to not only have innovations in the solutions, in the computer science solutions, in the AI solutions, and also the use inspired solution, but we are able to actually put them together to make it work. So what I'll try to do in the next part, I'll try to show you some highlights. Okay, I'll not have time to go over entire thing. um, like over the last 4 years, we have published almost like a close to 200 to 250 papers. But in addition, we have actually put them all together. So I'll try to show you some highlights, how all these components are working together with innovative approaches. I'll touch a little bit about the digital agriculture, then animal ecology, food transportation and security, and then we'll go down and select some aspects of the cyber infrastructure and AI components. I'll talk about the software release and training catalog and current collaboration. And we are always looking forward to more collaboration. So if you take a look at the digital agriculture, there are so many challenges. I just introduced you in the very beginning, just one of them, like a disease detection. But if you talk to the agriculture or agronomist or even the farmers, you will see the left hand side. These are all the issues the farmers actually deal on a day-to-day basis, like how to determine residue cover on soil surfaces, what is the soil aggregation size, how the crop is developing over time, non-uniform emergence. Like here you can see like a this is a non-uniform, like a some plants are not growing, whereas some other plants are growing, nitrogen deficiency, defoliation, and then the crop blight. So these are the kind of the problems. And now the question is, okay, how do we convert these problems into AI and then have the solutions, and not just have the solutions, but link it with the appropriate drones, the tractors, and all, so that you have the entire crop management in your hand, and you can actually take corrective action like selective spraying, nitrogen use deficiency, yield estimation, the plant replant decision, tillage control, etc. So as you can see from the left hand side, we have the problems, right hand side, we have the solutions, and that's what we are trying to bridge the gap through the ICICLE. So to achieve this, we have actually introduced a very interesting workflow. Okay, so in this workflow, you'll see it's a very generic workflow, like a focusing on 4 phases: data collection and pre-processing, model training, inference, and visualization. But more interesting thing is that we have developed this in a modular and configurable manner, and at the same time, it also demonstrates plug and play. So think of like the Lego boxes you would have seen. The Lego boxes has different pieces. So using those pieces, you should be able to build any one of your like a different kinds of the structures. And that is the kind of the idea what we have used here. Now, of course, different kinds of solutions exist in the community. For example, if you go to John Deere, which is the largest like a agro company, in the US, they have some solution, but it's very hardware. It's very hardware to their product, their solutions, and they charge quite a lot. Okay. Similarly, if you go to like let's say in the AWS, they will say, "Oh, we have a digital agriculture pipeline. You can work," but that is again hardware. So, so what we are trying to do, if you remember, our objective is to democratize the AI. So we have designed this in a modular manner. And for example, you as a researcher or let's say a company, you have a better inference data processing. So what you can do is like you can replace our C2 with your C2. Okay, so that is the kind of the goal we are having, so that over the years people should be able to plug and play their components, like take out our components and use their components in the best possible manner. So, and that is the way we think that it will continuously try to grow. And and in addition, like in addition to developing this entire solution, we have actually trying to standardize it in the way things actually work. For example, there are different ground data collection, either over a wired network, wireless network, different methodologies. How do you generate some standard shape file, and then also interact with the other devices. So this one is going to go into much more detail here. So we are actually keeping a track of the development of these technologies, the actual agricultural equipment and all. So we provide all these options, like whether you can do a ground-based, either you can do wired or wireless or aerial. All these are happening in a plug and play manner. You can also do like a model training at the AI edge for the lightweight task. Otherwise, you can send it to the cloud. We have some model commons repository, data commons repository I'll be talking about. You can actually do post-processing, and you can also trying to really enable this kind of the drones and all to really take the action. So what we have done, this actually this workflow is currently available as a service. We call it like an AI as a service. So in fact, one copy is running on the San Diego Supercomputer Center, another copy is running on the Ohio Supercomputer Center, and we are trying to deploy one more on the cloud. So the broad idea is we call it like a BYOD. Okay, D for data. That means we don't want to take your data. So we are providing this entire thing as a service. So you bring your own data, not beer, not like a Friday party, you bring your own beer. You bring your own data and interact with our system and have the training, have the data cleaning, have the visualization, have the inference, everything actually being done with while interacting with our system. So in the next slide, I'll actually try to play. This is a very short video of this entire system, which we call Harvest. And let me play. I think uh, you should be able to listen to it.
The Harvest Cyberinfrastructure streamlines the entire workflow. From the Harvest website, choose Data Collection and create a new job. Select the compute system and enter the destination path for your files and hit Submit. You will then be redirected to the OpenPass to launch a digital agriculture metadata mission. OpenPass handles everything from generating the flight path to flying the drone to moving the data to the HPC system through integration with Tapas. Harvest also has the ability to perform data movement from edge to multiple cloud platforms as well as cloud to cloud through integration with ArrayMorph, our optimized data transfer substrate. ArrayMorph is able to move data to one or multiple clouds seamlessly. It can even perform data transformations on the fly, giving us the ability to reduce the overall amount of data being transferred, thus significantly speeding up the performance. Now, let's turn data into results using the power of AI and HPC. First, we define the weeds to be detected by entering the labels and their corresponding search terms and an appropriate detection threshold. Multiple labels and search terms can be added. The job is scheduled on the HPC system. Our model scans the imagery, identifying and categorizing weeds across the field, producing a detailed inference result that is parsed to create a shapefile. We then set the grid size for the shapefiles, determining the precision of our spray zones. Harvest generates shapefiles for each weed type available for download by the user. We then are now ready to perform the crop intervention. To achieve this, we upload the shapefile generated by Harvest to the crop intervention platform, either an aerial drone or a ground-based spraying system. Here we demonstrate the process of uploading the shapefile to an automated spraying drone. With shapefiles in hand, it's time to take action. The system guides the sprayer to the exact location of those pesky weeds, delivering spot spraying with unmatched efficiency. As shown on the map, the drone follows the routes marked in blue. The solid blue lines indicate the segments where spraying is required. The dotted blue lines show the transit legs between spray zones, during which the drone does not spray. The solid green lines marks the area already treated. Together, these markings depict the planned spray path, the non-spray transfers, and the completed coverage. No waste, no guesswork, just results.
So
The
as you
hard
saw, this actually we demonstrated it at a farm science review 2 months back in Columbus, Ohio. That is one of the biggest event takes place at the Ohio State University, agricultural related issues. So there were a lot of vendors were there, and in fact, once some of the vendors saw our solution, some other vendors were very interested. Like a drone company was interested, and within like 2 hours, we were able to actually have our solution running on their drone. Okay, so that is the kind of the capability on which we are developing this so that it can actually be moved around, plug and play across a lot of different agriculture equipment. So then let me go into our second use in smart science cases, the animal ecology. So here, if you see the biodiversity these days is a very big issue. We human beings are trying to understand like how the animals also live and behave in our on the earth. And typically, what has happened over the years, like the state of the practice is that a lot of these animal ecologists, when they actually go for field trips, you might have heard of like going to Kenya or going to some Pacific Ocean to study different kind of animals. They go through they do a lot of data collection, come back, and then they come up with some hypotheses, and then they do study, and then come up with some results. But in this case, actually, it's sometimes they are not using AI. Sometimes it doesn't scale. They are not leveraging the computing continuum. They are not a plug and play solution. For example, if during the data collection, if they have just collected some garbage data, once they come back from the trip, nothing can be done. So we are trying to actually reverse the thing. We are trying to actually bring AI to get with them when they go on a field trip, how they will be using like a data collection, capacity planning, model training, field deployment, and post-study analysis. So they go hand in hand with our AI-based solution. And what we have developed here is actually we did a lot of joint work with one of the safari called the Wilds, which is one of the largest safari in US. It is actually in like a 20 miles from Columbus, and not only we have worked with them to have the solutions, and they are actually trying to adopt our solutions in some of those things. So here is again a video. Let me play.
The ICICLE ecosystem enabled the Smart Fields team to conduct a groundbreaking multimodal wildlife monitoring study at the Wilds Conservation Center in summer 2025. Beginning in February, we engaged with leadership at the Wilds, North America's largest conservation center, to deploy ICICLE's integrated sensor network. In June, we convened researchers from MIT, Princeton, University of Pittsburgh, University of Cincinnati, and major biodiversity organizations, including Conservation X Labs, Wildlife Insights, the Nature Conservancy, the Imagomics Institute, and the AI and Biodiversity Change Global Center. This group agreed on the need and value for an AI playground for animal ecology research. As a proof of concept, we designed and implemented an ambitious multimodal study that ran from July through August over a 220-acre enclosure. Our study tackled significant technical challenges in use, inspired CI from data harvesting to edge computing to multi-sensor fusion. The Smart Wilds dataset is a first of its kind for animal ecology researchers. We deployed camera traps, bioacoustic monitors, and flew multiple drone missions, capturing over 20,000 files, 100,000 animal detections, and synchronizing 101 gigabytes of multimodal data. The dataset was published at the Imagomics workshop at NeurIPS 2025 and released openly on Hugging Face under a CC0 license.
The wilds is a wonderful resource for us where we can do research on exotic endangered species such as rhinos, giraffes, grubby zebras, but there's also a ton of biodiversity and conservation going on here as well. This allows us to use the wilds as a testing ground to try out these new technologies, understand which sensors work really well, which don't, and how these different techniques can complement each other to deepen our understanding of the natural world and better inform conservation policies. We're out here to establish the wilds as a long-term biological field station, putting up camera traps, bioacoustic sensors, flying drones. Taking field recordings, all to create a rich multimodal data set to get a very granular view of what is going on out at the wilds. This project is the first of its kind, using all of these different sensor modalities to get a really close understanding of how these animals are using the landscape.
Our stakeholders at the wilds are already extracting valuable insights. They now have quantitative evidence of grazing hotspots and behavioral patterns for their Pear David's deer, the only breeding cohort for this species on the planet. Our study confirmed crepuscular behavior, with peak activity occurring between 5 to 7 p.m. However, the camera traps didn't capture early morning activities. Acoustic sensors were needed to track full behavior. Later, we will discuss new ICICLE CI that connect edge sensors into network systems, allowing acoustic sensors trigger drones or adjust camera traps for better coverage. Another interesting analysis found that Pear David were active at the same times as the Canada goose and grasshopper sparrow. Given the unique biodiversity profile of the wilds, we suspect these species have not interacted historically. From the Cyberinfrastructure perspective, this study demonstrates deep integration across the ICICLE ecosystem. Rather than isolated components, we orchestrated a complete end-to-end workflow. Computer vision models came from the ICICLE Model Commons, developed by colleagues in other thrusts. We integrated these with Harvest digital agriculture pipelines for labeling. Autonomous drone operations relied on our published software pilot, OpenPass, and WildWing tools working together for mission planning and execution. This integrated deployment validates ICICLE's vision of composable, interoperable components that create capabilities greater than the sum of their parts. The Smart Wilds deployment served as a test bed for two exciting new cyber-infrastructure capabilities that exemplify ICICLE's core principles. The Backpacks project embodies our CI4AI approach, using cyber-infrastructure to improve artificial intelligence capabilities. We realized that edge sensing components could be significantly more powerful when networked together. Our backpack system integrates multiple ICICLE components. It pulls detection models from Model Commons, uses custom camera trap detection software we developed with the MLR3 framework, and coordinates with WildWing and OpenPass for drone control. When vision models connected to the camera trap detect specific animal activity, the networked infrastructure triggers the drone to launch, fly to the camera track, and track animals present, providing behavioral observations that a fixed camera cannot capture. The backpack system could also work in reverse, using drone surveys to configure camera trap placement and sensitivity. By networking edge devices, ICICLE can support AI-driven adaptation in real time to ecological events.
So as you saw, like this is the kind of the things what we are trying to do in the animal ecology. So let me move to the food transportation and security. So here again, we are trying to do like a multiple sub-thrust. Here we are trying to do on a food supply chain modeling, food equity and access simulation, food logistics and data privacy protection. So let me touch a few of these. So one thing is happening, as you know, these days, like we go through a lot of different kind of scenarios, kind of the calamities, you may say. But at the same time, we need to make sure that the food flow is happening on a continuous basis. So here there is in US, there is a database from every county, how much food is actually going to the other county. Okay. So this data has been there in a lot of databases. So we have taken the data and then actually build a GNN based AI model. Okay. And with that model, now we can actually ask a lot of what if questions. Like tomorrow, if the example I gave earlier, like a freeway 5 from San Diego to LA, something happens, some big catastrophe happens, within like a 24 hours, what will happen? You can actually ask this kind of a put flow. The modeler, same thing, like a hurricane is coming. So let's see a short example of of this uh, solution. Let me play. I believe there is a video here. Yeah.
Hi everyone, my name is Chen Zhang. Today I'm excited to introduce our graph neural network-based food flow dashboard. Let me start with a story. Have you ever wondered where the food in Franklin County comes from? If you look at the meat category here, most of the inflows are from the nearby states. In fact, the top 10 counties together contribute about 7.9% of the total estimated flows. This shows how much the local food supply depends on the condition of the nearby highways. And if you are interested in other food types, including agricultural products or milk products, you can also check out here. Now, let's zoom out to the domestic food flows across the United States. By default, the map shows Los Angeles County, which serves as a key transfer hub for food supplies. This means that whenever events like a wildfire occur, food security in the region could be at serious risk. With our dashboard, users can easily switch between the food categories, as well as the original county, destination county, to explore whatever flows they care about. And if they need the data, they can also download the filtered data directly from the download page. Finally, let's return to the story page again. If you are curious about...
So let me move ahead. So this, you can see the kind of the things what we are trying to design, so that we can actually bring this kind of solution to the end user. So the other thing what we are doing here is a food equity access simulation technology. So this is very important. Many times you might have heard, like in your neighborhood, all of a sudden a grocery store wants to close the branch or that shop. But then the question is, okay, what happens to the food access to all the households nearby? Of course, if there are rich people there, it will not hurt them. But if there are poor people, they don't have any cars, there are too many family members, they will be in danger. And this is how a lot of like a government officials, municipalities, the city government agencies, they want to actually understand this. So to enable this kind of things, we have developed this called a feast. Again, there is a small video here. Let me play it.
When they access Feast for the first time, they will see a map. This map includes the uploaded food access data for the local government's chosen area. In the bottom left corner, there's a legend. This identifies key icons on the map. The blue hexagon indicates a supermarket, and the blue triangle represents a convenience store. As the model improves and expands, the legend will include a wider variety of icons. This may include farmers markets, ethnic grocery stores, mobile markets, and more. Next, the legend lists 3 house icons. These icons are color-coded based on their food access score. Green signifies the highest or best food access. Yellow signifies the middle, and red signifies the lowest access. The data included in the simulation is sourced from the American Community Survey. As the model progresses, Feast will support users in adding more data from other sources. We ensure the model that users deploy is complete by integrating data and variables of the user's choice. You'll notice that there are zoom in and zoom out icons in the top left corner of the screen. As you zoom in, clusters of homes break apart into more granular data. This allows the local government to view the average food access for a small neighborhood or community, as well as an individual household. When you click on a household, you will see multiple variables, including income, household size, vehicles, food access score, and more. Now, let's look at using the Feast tool. In the blue bar on the left, you can click Remove Store. For a local government, this allows them to simply select the closing store from the drop-down menu and click Submit. After clicking Run Step, they will be able to see which populations are impacted and how severely. This data will be helpful to visualize and understand in order to better plan for addressing food insecurity in the face of a store closure in food access.
So
Feast
let me move ahead. So similar things you can do, like add a store, add multiple stores, remove multiple stores. So in a fingertip with very small response time, anybody can actually analyze what will be the impact in that community. So the other thing what we are also doing we have developed a food security sandbox. So this has a lot of let's say we collect the data from a lot of farmers. Farmers can actually find, interact with this environment, and then find similar farmers. Look like a public link to public private data set for farmer, link public private data set for food security, farm to fact production data. A lot of these things, the most important thing is the privacy preserving. And that's what we have done. This entire security sandbox we have developed so that a single farmer may get aggregated information from others, but he or she may not be exactly knowing who else is contributing the data. Okay, so that's how we actually want to have this kind of like a federated learning, privacy preserving technique. So these are some of the use inspired science cases. Let me quickly go below and then show you like how we have designed the CI and some of the AI components. So to bring all these things together, I'll highlight first the unified reference architecture, and then I'll talk a little bit about the models and data commons. So as you can see, in all these inspired science cases, we want to put entire workflow. There are so many components. As of now, like we have almost 150 components. We are working together, and we want to make sure that they all work together. So we have, over the years, we have really come up with a reference architecture so that every time we introduce some new component, we need to make sure that that actually fits into the ecosystem. And you saw this example earlier in the annual ecology slide. So this is how we have done. At the top level, we have the workflows and pipelines. We have a model commons, data commons. Then we have the end-to center IoT data management, and we have some of the intelligent middleware and tools which are trying to actually analyze what is happening on this entire end-to-end workflow and to improve on it. This is the AI for CI component I indicated earlier. We may not have time to go over it. Now, the other thing what we have done, this is very interesting because now we have so many models, so many data sets. So how do we actually put them all together, or as an end user, how quickly they can actually identify and to make sure that this model and data playground is working? We also want to optimize all these models using neural architectural trust search. And the final thing is like, how do we make our entire system working in a trustworthy AI manner? So first I'll try to provide this provisioning model and data common. So this is how we have actually stacked, as you can see, in a layered software architecture. And this is a very dense slide, but that's how again shows the complexity. So within this, we have the data playground and the model playground, and let's see some of the features to highlight. So here we'll be seeing like the model and playground, like a Tapis workflow. There is a ML hub, democratization AI. There is a Patra model card to keep the provenance information as we come with the models, and then we have the playground. So let's see again, there is a short video here.
AI model discovery is broken. Researchers spend hours hunting across Hugging Face, GitHub, and institutional repositories. And even when they find something, there's no guarantee it's reproducible or trustworthy. I'll show you how ML Hub and the Patra knowledge base solve this, and how we're using agentic AI to make model discovery as simple as having a conversation. ML Hub provides a unified API layer for the full model lifecycle: discovery, training, and inference. For discovery, researchers can find models and datasets across Hugging Face, GitHub, and ICICLE's own models through the Patra knowledge base, where every model has a model card in our knowledge graph for accountability and reproducibility. What makes this production ready? Each model version has its own set of artifacts that can be deployed to isolated inference servers and containerized environments. Researchers can go from discovering a model to running inference without leaving the platform. But we've taken this further. Instead of researchers needing to know which model to search for, we built a playgrounds agent that understands their workflow. A researcher describes their problem in natural language. The agent reasons about what they need, queries ML Hub, which queries the Patra knowledge graph, and returns not just a model, but why that model fits their use case. Let me show you. Here's the playgrounds agent in action. Carlos, an animal ecologist, introduces himself and describes his research, studying animal behaviors through thousands of camera trap images deployed in the wild. Rather than just returning search results, the agent asks clarifying questions. What's your primary goal? Do you need detection, classification, or behavior analysis? Carlos explains he needs to automatically detect animals and ideally classify species. The agent queries ML Hub, which searches the Patra knowledge graph for ICICLE models matching his use case. Within seconds, it recommends megadetector V6B. It provides performance metrics, licensing information, and explains exactly why this model fits Carlos's workflow. But it doesn't stop there. The agent proactively notes that megadetector handles detection, not AI
So
model.
I'll again move forward a little bit because we might run out of time. So similarly, we have done a neural architecture search. As you know, once you have a model, the question is that the model, how much time it is taking, can we still optimize? So that is the field of the neural architecture search. So here we have a small video, but I'll skip.
Neural architecture.
The final thing what we are trying to do here is that how do you make sure your model is trustworthy? That means when you are building a model, the thing is, do we take all the data or do we throw away some of the data which actually doesn't conform to the correct parameter? So let's see two components here, and then we'll try to close.
AI is increasingly used to make critical decisions, but it can fail silently and confidently. How do we build AI systems we can truly trust? At ICICLE Model Commons, we've created a two-part ecosystem that builds robust models and ensures they make reliable decisions. Ohio's rich biodiversity provides a critical barometer for the health of our ecosystem. To monitor it, ecologists are deploying thousands of camera traps, creating a fire hose of data, in this case, hundreds of images from this one video. AI promises to help us make sense of it all. This rich data forms our train time data distribution. However, once our model is trained, in deployment, the data it may encounter might be very different from the training data. That is, out of distribution, causing failures. Our first project, Forte, is the gatekeeper for this data stream. Forte asks a fundamental information theoretic question. Is this image typical of our trusted, high-quality data? A camera trap doesn't just capture the white-tailed deer we expect. It captures lens flares, rain-streaked blurs, and unexpected visitors like a neighborhood cat. Feeding atypical or out-of-distribution data directly to a classification model can corrupt analysis, leading to flawed population models and misguided conservation policies. Robust filtering is needed before classification due to conditions like motion blur and low-quality images. Forte maps each image to a high-dimensional feature space. Here are the original data points from our reference dataset. For each new test image, Forte calculates the kth nearest neighbor distance. Forte then constructs a Euclidean ball around the test point with this as the radius, thereby creating an uncertainty set by taking the union of balls around each of the k nearest reference points. Forte uses 4 summary statistics: precision, recall, density, and coverage to measure typicality. Forte generalizes. Here we see images collected from the OSU Small Animals dataset. Forte successfully identifies in-distribution data specimens with or without the presence of animals with a green checkmark. When encountering unclear or degraded footage, Forte flags it clearly and signals to stop trusting the classification output. This is crucial in challenging conditions with unseen data points, like low visibility and poor quality imagery. Forte offers the only data-centric algorithm that requires no class labels, requires no exposure to atypical data, has no restrictions on the architecture of models.
So as you can see, this is the kind of the things what we are trying to do within the cyber infrastructure, within the model commons, to make sure that what we are building is actually very robust, trustworthy, and then people can actually use. And as we are developing these, as I indicated, we have up to 114 components have been released so far. So if you go to our ICICLE GitHub, you should be able to get it. And these are the kind of the very statistics. But in addition to our ICICLE Hub, every sub-project have also their own GitHub. Okay, and we take periodical snapshot from those GitHub. So of course, a lot of users download from those GitHub sites, and which we cannot track. So as of now, quite a lot of users have started actually using these. in addition to these component software components, we have developed two nice things. One is called a component catalog. How exactly these components are being put together, that actually helps not only our ICICLE researchers but also the outside researchers. And in addition to that, we have also training catalog. So if you download a component and you go inside, it actually has documentation for all the related presentations, the videos and all. And that actually helps very easily for a newcomer to actually start using it. And one example here, Mary actually used this in one of our summer courses with a lot of high schoolers, and they were very in a very short period of time, I think within a few weeks, they were able to understand these components. These are high schoolers, and were able to run some of these components on the STSC Expanse and all the supercomputer centers. So you can see, like, this is the kind of again the direction we are trying to go. Not only we have very robust solutions, but we are trying to reduce the barrier and make it simpler for people to use. So with all these components, let me close. As of now, like these are like a 58 organizations from 9 countries are using our stack. If you're interested, please feel free to go download our stack. There is a registered button there, so you can do that. And as I indicated earlier, ICICLE is the AI institute which has been responsible for developing this cyber infrastructure. So we are working with other ICICLE institute like AI for All, Agate, IRA, and other HPC centers to make sure that they're also facing the same problems, but instead of them developing, they can actually try to utilize our solutions. We're having collaboration with a lot of industry, non-profit. Some of these things are going on, they're maturing, like the Tata Consultancy Service, Apple Farm, Conservation X Lab, and the Wilds we heard. We are also going international. There are a lot of discussions going on with India and UK. So broadly, we are looking forward to collaboration if you're interested in some of these, the software components. So with this, let me conclude here. So what I broadly indicated that this kind of the computing continuum is the new way the data is coming. And we are trying to ICICLE is developing all the necessary cyber infrastructure in a configurable, adaptable, and plug and play manner. And our vision is that even though we have just verified or developed the stack and verified with 3 of these verticals, but our solution can be actually be extended to health and medicine, environment, communication, mobility, etc. Because all these communities are facing exactly the same problem. So our stack can actually be utilized for them. So with this, I'd like to thank. These are all our ICICLE participants who have actually contributed to this. And with this is my email address, and I'll be very happy to take questions from you.